Our next two presenters both come to us from IBM Research. So that's Dr. Xiaokui Xu, who leads their Cyber Reasoning Initiative and is a member of the Association for Computing Machinery's Future of Computing Academy. And Dr. Jiang Zhang, who is a principal research scientist and runs IBM Research's cybersecurity intelligence team. Security analytics is one of his research focus areas. And they're going to be talking today about their purpose-built language for threat hunting. They call it Kestrel, and how using a common language enables documentation and collaboration between threat hunters, even at different organizations. So Dr. Xu and Dr. Zhang, we're all looking forward to hearing what you have to say. Thanks for being here.
Thank you, David. Good morning, good afternoon, and good evening. Welcome to our talk on Castro. Castro is an Open Cybersecurity Alliance project we announced 3 months ago at RSA Conference. Today, Jiong and I will give a brief introduction to Castro for you to understand its basic concepts and get you quickly on board to compose your hunt from simple hunting steps, execute your hunt across different environments, and share your hunts with your colleagues and the community. Threat hunting is an exciting task, especially when you connect all clues and uncover a stealthy attack campaign. You are the superstar. However, the journey of hunting may not be smooth. Even for the same TTP you try to verify, you may end up with learning and writing different queries to different data sources, not to mention all the overheads of understanding the returns, writing adapters to glue hunt steps, forking a hunt flow for different possible next steps, and merging data from different operations. If we can enable high-level hunting knowledge reuse from yours and others' previous hunts, and if we can define each hunting step cleverly so they can be appended to each other without adapters, we can make hunting much more efficient and much more fun. Welcome to Castro, a language for threat hunting. When you write a C program, you don't need to know instructions on different architectures, x86, Power, or ARM. When you write a Castro hunt, you don't need to know how a TTP match is done on Carbon Black, CrowdStrike, Sysmon, Curata, ArcSight, and more. And you don't need to worry whether the output of a Carbon Black query can be followed by a Splunk query or a VirusTotal threat intel enrichment. Kestrel provides you an abstraction to describe hunt steps and connect them into hunt flows. The description is based on entities like processes, files, users, network hosts, etc. We call these entity-based cyber reasoning, which we will demo and further expand. In other words, the Kestrel runtime in the blue parts encodes a lot of basic static domain knowledge, such as how to match a TTP against a specific data source and how to connect two hunt steps. So humans in the red parts can focus on the intelligent, innovative, and exciting part of a hunt to uncover stealthy threats. Okay, we already mentioned two basic concepts, hunt step and hunt flow. Let's have 3 examples of common hunt steps before we discuss how to write or compose your entire hunt flow or hunting programs. The first common hunt step, match a TTP pattern, schedule task in Windows. There are tons of ways to implement a schedule task in our operating system like Windows or Linux, and these ways changes with system upgrades. The blog on the right explains the widely used way of doing it in Windows 10. Basically, register a service in the system and the Windows Service Manager will launch a task at scheduled time. So how do you describe the TTP to match? Let's launch a Kestrel hunting session in a Jupyter notebook to find out. The simplest description of this TTP is just 2 words: scheduled task, which is simple but too vague. We need something more concrete for a machine to interpret. Kestrel implements entity-based cyber reasoning, meaning we describe everything on the entity level: processes, files, network traffic, etc., and the relationship between them. We can describe Windows service processes, which simply has process name as vchost.exe. We can get all such processes into a Castro variable as vchost. And then we can describe a subset of svchost that focus on scheduling services. We call such processes scheduler. If we can get all scheduler in the system, then we can find all scheduled tasks as their child processes in our next common hunt step demo. The second common hunt step is to find connected entities. This is done through the Kestrel command find. The reason to have a dedicated command for this, as well as the relationship diagram shown here, is because of the complexity we try to mask out. First, different data sources and intermediate layers use different terms and mechanisms to describe and store the same relation. Second, the data returned from data sources are records, such as a line of log that Nginx accepted a connection from an IP address. Based on that single line of log, if the user asks the parent process of the Nginx, how can Kestrel find out? It can't. Actually, a Kestrel command will generate code that is much more than just what the user described in a hunt step. Kestrel proactively fetches log records and assembles them into entities before presenting the results to the users in Kestrel variables. So let's use find and not worry how the underlying layers describe and store entity relations in disconnected records. We will continue from where we left in our first demo. Let's re-execute the first 2 hunt steps in one code block and create Kestrel variables svchost and scheduler in this new hunting session. The remaining task is to find the child processes of scheduler, so we will review the schedule task on the monitored machine, host 101. We can do that using the find command. And then we can display the processes in the task variable with its names, command line, or any other attributes. Okay, we get 18 different processes as scheduled tasks on the machine within the time range that we specified. The third common hunt step is an analytics step, which is the execution of a foreign language module that satisfies Kestrel hunt step input and output rules. An analytics can be written in any language. Even a proprietary software can be encapsulated into a Kestrel analytics step. We currently have a Docker interface for executing analytics steps, and native Python interface and AWS Lambda interface are on the roadmap for running analytics in different environments. On the top is a screenshot of our Kestrel analytics repo, which hosts community-contributed analytics. Currently, we have analytics doing threat intel enrichment, anomaly detection, visualization, and more. Let's check out an example to find geo-locations of IP addresses and ping them on the map. You can find the exact analytics in this demo by cloning the repo. We will start the hunting session by loading some data from one of our previous hunts into a Kestrel variable NT, meaning network traffic. The previous hunt here is actually our RSA demo Jion will show in a few minutes. We display the source and destination IP and port for the loaded network traffic. Then, let's see where the destination IP addresses are by applying the ping IP analytics from the Kestrel analytics repo. Now, we have the geo-locations of IP addresses found and pinged on the map. Okay, after we get some ideas about individual hunt steps, an important question is, how can we put hunt steps together into a hunting program? We may want to do a pattern matching followed by an analytics, or a pattern matching after another pattern matching, then an analytics, then another analytics. Oops. Threat hunting is an interactive way of programming. You never know what hunt flow is the right one to detect the unknown threat. So you may change any hunt step in a flow frequently, like this. And you may merge the results from two flows into one. Or you may fork hunt flows. We designed the Castro language carefully so the output and input of a hunt step are both Castro variables or a list of homogeneous entities. This enables freestyle hunting flow composition from individual hunt steps. What does a hunt flow look like in the real world? You may start from the gray part of an initial threat hypothesis, maybe a typical ransom on a server data. Then at some point, you'll find the attacker may encrypt images on a phone instead of servers in the cloud. So you branch out to verify threat hypothesis variant 8.2 on the yellow branch. However, both hypotheses may not conclude, and then you start to think about the possibility of data exfiltration. The spams, the exploits, and some lateral movement at the beginning of the gray flow are real. So you reuse the first few steps and branch out from the gray flow to develop the data exfiltration threat hypothesis in green. After the threat is found, you can clean up the hunt, share the Jupyter notebook or the Huntbook with your colleagues or the community using the Kestrel Huntbook repo. Can you run your previous hunts on a new customer? Can your colleagues run your hunts not against Carbon Black but Sysmon? Can you be recognized by the community for publishing state-of-the-art hunts that others can download and run? Next, I will pass it to Jion to explain how we support different data sources in Castro.
Okay, thanks, Xiaokei. And at this point, some of you may start wondering about how we actually operate across multiple data sources. And some of you already noticed from the syntax, the Castro showed during the demonstration, maybe already noticed we are using the sticks. Sticks meaning the structured threat information expression. And sticks is an actually open standard maintained by OASIS, Cyber Threat Intelligence Technical Committee. And the sticks is used to exchange cyber threat intelligence. And sticks patterning is a patterning language supporting sticks indicators with rich set of operators to match patterns. And also you're using the cyber observer expression called cybox to describe events of the stable properties, such as indicator patterns. And we elaborate sticks in Castro for two reasons. And as Robert also emphasized in his talk, and we strongly believe the open standard and open community can be a way to facilitate information sharing across multiple organizations And that's also helped to protect against ever-evolving cyber threat together. And second, our empty space reasoning, which I can explain only part of the talk, is actually fits well with Stick's graph-based model in this diagram, and which can connect various heterogeneous observables with their relationship. Let me try to move. Okay, thank you. And Stickshifter is an open source project hosted by OCA, Open Cybersecurity Alliance. Some of you already heard and maybe already using this. And this is a great open source project to enable universal data access using Sticks patterning while data stayed where it is. So for example, as shown on the right-hand side, a single Sticks patterning at the top can be translated into multiple native queries at the bottom through various Stickshifter connectors to communicate with multiple data sources like EDR or SIEM and data lake. And then query results are returned back as the Sticks observation in this format. So in other words, Stickshifter is a great way to kind of integrate with multiple products. And for single Sticks patterning can be used to interact with many different products. And as you can see in this chart on the left-hand side, today Stickshifter already supports many different data sources, so you can directly using it, and it actually continues evolve with open source community. That's the beauty of the kind of the community effort. That's why we also open source the Castro. Okay, and we are going to demonstrate how we can do the threat hunting with Castro hunting language to discover data breach started from spear phishing email. And in this diagram, as you can see, a threat hunter on the right-hand side relies on observation from a few vantage points to discover the whole attack plot marked in the red color. And using the real-time host or network-based kind of the monitoring solution, which you might already using in your day-to-day jobs. For example, Sysmon for monitor Windows machine, and open source system telemetry called the Sysflow for monitoring on maybe the Linux server, and a Skid web proxy for monitoring the web traffic. And these logs are ingested into Elasticsearch or maybe SIEM system. In our demo, we are going to use the QRadar, but which we can utilize and correlate using the Kestrel hunting language. And actually the full version of the demonstration, our video is available at the YouTube link at the top. And we are going to also post the link after the talk. And today, due to time limit, we are going to just walk through a shorter version of the threat hunting demonstration video. Hopefully the video, the audio volume is good. Let's see. Let's start threat hunting with our Kestrel kernel in Jupyter Notebook. In StarX, Node.js server is running on a server machine. Let's inspect the server log to check if there was an exploit attempt to the server. For that, we can easily connect with the data source via Stickshifter, where the Sysflow server logs are stored. We can describe an exploit TTP using Sticks patterning. Basically, the parent process is Node.js, but the process is not associated with the Node.js. By inspecting exploit node variable and its child process using find command, we can confirm an exploit attempt followed by a reverse shell on a machine. We can further see other various activities on a machine after the shell drop. Since there are so many process activities on a machine, we can apply analytics such as suspicious process scoring to quickly identify the most suspicious process by sorting based on suspicious score. It looks like tweet process was the most suspicious process on a machine. Then we can check the network traffic using the find command that was generated by this most suspicious process. Interestingly, the destination was actually web proxy. This means that we need to correlate web proxy log to discover the real destination address. So using Stickshifter, we can correlate with the web proxy log to find the real destination of the network traffic. Then you can further enrich the data by applying various analytics. For example, enrich domain analytics to correlate with who is information to find the more information about the IP address, and exfiltrate risk rating analytics to assess the exfiltration likelihood of the network traffic. Such additional information is captured in the Kestrel variable as extended attribute. This seems to be a case where internal data from network stories is exfiltrated to outside social network. Besides a forward impact analysis, we can also conduct backward root cause analysis. From exploit node variable, we saw there is a network traffic coming from internal employee laptop. Let's do cross-host data correlation using Stickshifter and Sticks patterning to find out further details. From the laptop logs captured by Sysmon, we can locate the PowerShell process generating the network traffic. By further inspecting its parent process using the find command, we can identify it was actually due to WinMail process. And then we can also see other network scanning activities from there. So in summary, with Castro, we are quickly able to conduct correlation across multiple hosts and data sources, such as Linux server, Windows laptop, and web proxy logs, and examine process and network traffic logs with inline analytics. All right, so as we just demonstrated, Castro hunting language actually enables threat hunting across multiple hosts and the data sources. And at this point, we'd like to invite all of you to join our OCA Slack channel using the link in the chat to meet other threat hunters and share your thoughts about threat hunting. And we strongly believe the building and engaging with the community is a good way to be empowered and contribute back to the community. And that's why we open source Kestrel and build the Kestrel on top of the open standard. And you can start using the Kestrel in your environment by just doing the pip install and also maybe the cloning the repository to further development and following the step-by-step hunting tutorial on our blog posting and to quickly testing on your data set. And also you can further learn from more experienced threat hunters by adapting their hunter flows, and or you can contribute back to the community by sharing your own hunting patterns and advanced hunting analytics with your community, and also contribute to the Kestrel runtime development. And our OCA Slack channel and the Git repository is a good place to where you can engage with other threat hunters. And here are the few resources and references for Kestrel. I know there are many of the URL, but you don't need to remember all of them. You just need to bookmark our main repository, the main GitHub repository marked in the blue at the top, and where you can easily find the links for other key resources and references, including the Kestrel documentation, tutorials, blogs, or demonstration videos and research papers. And we look forward to working together with many of threat hunters like you and to further innovate threat hunting methodology and build a strong threat hunting community. And we'd like to close by thanking everyone who has supported and contributed to the Kestrel, and look forward to talking with you in our Slack channel. And thank you for listening our talk, and we are happy to take any questions.
Thank you very much. Yeah, I think there in your hallway, there's been a number of people very interested in learning more about Kestrel, and also I have to say a number of shout outs to Stix in your hallway.
Okay.
I did have one question that I wanted to bring up is related to, you had some examples in your videos about bringing in, I think you called them foreign language analytics into Kestrel. And I think all the ones I noticed were basically by calling a Docker image. And I was wondering if you could say a little bit more about that, and also if it's possible to mix languages inside a Kestrel notebook and bring in R or Python or something like that.
Thanks for the question. That's a very good one. And as I mentioned, the analytics step is a way to use a foreign language in Kestrel. So you do not literally write a foreign language in the Huntbook directly, but you encapsulated that somewhere else. So you call it as a Hunt step. And currently we have the Docker interface for the analytics step, and we have on plan the AWS Lambda interface, so that we can provide a function as a service in the cloud, or a native Python interface, so that if you want to try to run some of the steps or your code that is in native Python. So you do not need to run a container if that is too heavy. And we have all the information in our documentation, and we have a figure that explains how we handle different data source interfaces and different analytics interfaces, how that relates to our Kestrel session manager. And one more thing is, we really try to make things simple so that even for people to not write a new analytics in Docker, but also write a new interface. So you only need to get one Python class and then maybe start 100 line of code, boom, you have it. So you can check all the information how to do that if you want to expand in our documentation. Thanks.
Thank you. Well, thank you again for your presentation. I think you have a lot of interest, and I think you're going to have some good chats in the Slack hallway. So appreciate it.